welcome to our Week 12 lecture for Math 351. I hope you're having a good Thanksgiving break. Today, I just want to talk about a few things that will come up in the Week 12 homework for y'all, okay? So the first thing is something we talked about in class, and that is, of course, the definite integral gives you the area between the function and the x-axis. But when the graph is below the x-axis, the definite integral gives you a negative number. When the graph is above, it gives you a positive number. So in a lot of the homework, they ask you to find the area. So what they're going to want is for you to find the area that's all positive. So you need to find out what part is below the x-axis and what part is above, and then split the integral into two separate pieces. So here's what I mean by that. Here we've got the function f of x is 2x minus 12. And if I graph that, you know it has a y-intercept of negative 12. And it has a slope of 2. And we want to graph this between x equals 5 and x equals 9. Well, if I put 5 into this function, I get negative 2. So let's call this the point 5 comma negative 2. And if I put 9 into the function, I get 18 minus 2, which is 6. So this is the point right here, 6 comma, 9 comma 6. And you see that if I calculate the definite integral from 5 up to 9 of this function, it's going to count this stuff on the left as negative and this stuff on the right as positive. So we don't want that. So what we're going to do instead, this is negative, this is positive. So what we're going to do instead is we're going to break this into two functions. We're going to find out where this graph crosses the x-axis, and you know that's easy to do. We'll just take 2x minus 12 equals 0, and that gives us x equals 6. So I'm going to break this into the definite integral from 5 to 6 of 2x minus 12 dx. Need a dx up there. We'll talk about what that dx means later on today. And then I'm going to break it into the integral from 6 to 9 of 2x minus 12 dx. Okay? Now, the first one should come out to be a negative integral. The second one should come out to be a positive integral. And yeah, when I integrate this, I'm going to get x squared minus 12x. I want to plug in the 6 and I want to plug in the 5, and then I want to subtract. So that's the notation we use for that. This will give me 6 squared minus 12 times 6 minus 5 squared minus 12 times 5. And this gives me 36 minus 72, that's minus 36. And that's 25 minus 60. And that's a negative 35. And so this gives us, you can see a negative 6 plus a 35 is a minus 1, but we want to take the absolute value of that. So that little area on the left there is a 1 unit. And then I take the area on the right. I get the same antiderivative, of course. Plug in a 9, plug in a 6, and subtract. So I'll get 81 when I plug in the 9, minus 12 times 9 is 108. Minus, and when I plug in a 6, I'll get 36, not 63. Minus 12 times 6 is 72. So I've got an 81 minus 108, which is a minus 27, minus a negative 36. And let's see, 36 minus 27, not trusting myself, is a 9. And so my final answer will be 9 plus 1, which is 10 square units. Okay. So that's all you need to do for those. Just find out where these things intersect, break it into two pieces, and then calculate each one. If you get a negative answer, take the absolute value, add those babies together, and you're good. Okay, the next thing I want to show you is what to do when you have a u substitution and a definite integral. There are actually two ways to solve problems like this, and I want to show you both options. Okay, so let's go ahead and start this off. I can see that this is kind of complicated, but I note that if I take the derivative of 4y6 minus 3, I get a multiple of y to the fifth. So that's a clue that I need to use a u substitution, and I'm going to let u be equal to 4y6 minus 3, and then du will be 24y to the fifth du. And let's see, the 4y to the 6 minus 3 comes in for this, and then what's left over is the y to the fifth dy. So I'll solve this for y to the fifth dy, and that gives me 1 over 24 du equals y to the fifth dy. So that's what's going to go in for the blue pieces. So let's find that antiderivative. 1/24 du, that's my y to the fifth dy, and then 4y to the 6 minus 3 becomes a u, and the u is cubed. So I'll have 1 over 24 times 1/4 u to the fourth when I evaluate the integral. Now, I can't plug the 0 and the minus 1 into this because the 0 and the minus 1 are y values. So in my integral up at the top, this really is y equals minus 1 to y equals 0. But my integral that I just calculated has a u in it, not a y. So I've got to convert this back into y's to evaluate this. So let's see, 1 over 24 times 1/4 is 1 over 96. And then my u, I'm going to use the same thing I used to substitute. I'm just going to substitute back. I've got u to the fourth. That'll become a 4y to the sixth minus 3 to the fourth. And now I can evaluate from minus 1 to 0. So I've got 1 over 96. When I plug the 0 in, I'll have 0 minus 3, so minus 3 to the fourth. Then I'll have minus 1 over 96. And when I plug the minus 1 in, let's see, minus 1 to the 6 will be a positive 1, so I'll have 4 minus 3, which is a 1. And this gives me 81 over 96 minus 1 over 96. And so that's 80 over 96, otherwise known as, let's see, 4 goes into both of those, so 20 over 48, 24. And let's see, 4 also goes into those, so 5/6 is my answer. So that's one way to work this problem. There's another way that is a little bit more sophisticated, and if you ever have to do these for another class, this is going to make you look smarter to your professor. So let me just put a little line over here and show you how to do this the second way. It starts off the same way. So we still have our integral from minus 1 to 0 of y to the fifth times 4y to the sixth minus 3 cubed dy. I do the same substitution. U equals 4y to the sixth minus 3. Du is 24y to the fifth dy. But now I go one step farther. I look at my limits of integration and I go, when y equals minus 1, u equals 4 times minus 1 to the sixth minus 3, which will be 1 when I plug that in. And also when y equals 0, u equals 4 times 0 to the sixth is 0, and 0 minus 3 is minus 3. And I change my limits of integration to match. So the minus 1 becomes a plus 1, the 0 becomes a minus 3. The substitution is the same as what I had before. So I still have 1 over 24 u cubed, which becomes 1 over 24 times 1/4 times u to the 4th. But now I evaluate by my new limits of integration. I don't have to go back and substitute back into y's because I've really done it when I do my limits. So when I plug in here, I've got 1 over 96 times minus 3 to the 4th is 81, minus 1 over 96 times 1 to the 4th is 1. So 81 minus 1 over 96 is 80 over 96. And let's just say etc. from this, because you can see at this point I've got the same answer that I had before. Okay? So just wanted to show that to you as an option. Either one of these techniques is going to work for you. You can use whichever one you like. But again, like I said, in future classes, if you've got a lab or something and you have to hand in a lab notebook where you need to actually do one of these calculations, the second one makes you look just a little bit smarter if you do it like that. But you don't need to. Okay? That's the second thing. Let's look at our third. I've got 2 more. Okay? This is very similar to the first question. If you have a piecewise function, you just set this up as 2 separate integrals. And I won't calculate this, I'll just set it up for you. Notice I need to integrate from 2 to 9, but this function changes formulas at 5. So you'll just integrate from 2 to 5, and you'll use the first function, and then you'll integrate the second function from 5 up to 9. So the 2 is down here, the 9 is up here, and the 5 is the dividing line. That's where I have to break it into 2. And then you'll just add your 2 pieces together. So I just wanted to point that out to you. And then I have one word problem I want to talk about. And it's not that the word problem is especially difficult, but I want to show you why these word problems get set up the way that they do. So when you're actually doing real life things with this later in school or in life, you will understand how to set these up or how somebody else set them up and be able to follow their reasoning and their work. So this is a question from the homework as well. It talks about a long study. Tree scientists conclude that a eucalyptus tree will grow at a rate of, 0.06 plus 4 over t plus 4 cubed feet per year. And then they say that t is the time in years. And then they want the total number of feet that the tree will grow in the second year, right here. So because it's this homework, you know that we're going to take the definite integral of that function. And that we're going to have some limits of integration. And we'll talk about those limits of integration in a minute. But here's what I want you to see, is that the units are going to tell you in a real life problem what to do. Notice this is in feet per year. And t is in years. So that tells us that this is going to be in years. That's the significance of the dt. It is the units that you're going to use to multiply by to get your feet per year. And so when you cancel your feet per year times year, you're really adding up feet. Okay? So that's what you're going to use to set these up in real life. Of course, in the homework, it's pretty obvious what you're going to do because they usually have like an r prime or something like that. You know that you have to go backwards from the derivative. But that's the reason that these are set up the way it is. That's also the significance of that dt or dx or whatever it is. It's the units that the horizontal axis are measured in. Okay, if t was measured in days, you would have a conversion factor to convert from days into years. That would be like doing a u substitution. That's a little bit farther than we're going to go here, but I just wanted to let you know that's how these actually work in real life. The other thing really quickly to set this up is we need our limits of integration in the second year. So I want the total number during the second year. So the second year starts at the end of the first year and ends at the end of the second year. So those are the limits of integration for that. And then for part B, of course, it'd be the same function, but you'd integrate from 2 to 3. And that's all. I hope you have a good break. Remember, I have a discussion question and I'll be putting up in the forums for you for this week, and that will be your participation. And your homework 12 is due when we get back. So have a good break. Take care. Bye-bye.